perhaps there are hidden portals to higher dimensions all around us. And you've read so much about high-dimensional content, but few people tell you where the higher dimensions come from. Now, this idea, which sounds like science fiction, has its roots in the minds of leading physicists. Then the next 30 minutes may append your understanding of higher dimensions. At the same time, I hope this video can bring you a cross-dimensional journey of physical and mental pleasure. High dimensionality is not just about fancy graphics in a video. On the exploration of invisible and intangible dimensions, it was coined by Theodore Karuza in the 1920s. The idea that the universe might be hiding extra dimensions. Even Einstein himself mused about it. But physicists still argue about him to this day. How does this Kaluza know the high dimensions, and where are these extra dimensions? What do they look like, and how can we find evidence of their existence? It all started in 1916, when the world was in the middle of World War I. However, it failed to stop Einstein's footsteps. He spent the last decade trying to take special relativity a step further. The most mysterious force in the universe. Attractive forces were also incorporated, and after several twists and turns, general relativity was born. This theory turns attractive forces into a geometric game of four-dimensional spacetime curvature. But it's also rarely maddening. It can be said that Einstein dropped a Wong fried, but few were able to catch it. It was then that a physicist named Theodore Kaluza entered this labyrinth of Einstein's equations. He wasn't one of the big names in physics at the time. He was obscure, but his curiosity about the universe burned like a flame. While he was mulling over Einstein's beautiful and complex equations, a bold, almost insane thought struck him like lightning. Since Einstein said that geometry is dynamic and at the heart of the physics of attractive forces, what if our universe had one more dimension than what we see? What would happen if Einstein's equations were written down in 5 dimensions of spacetime? At first it sounds like a silly idea or a mathematician amusing himself on scratch paper. After all, the world we live in, space has 3 dimensions. So look at Einstein's equations in 4 dimensions. Can it have anything to do with our real physical world? That's what most people think, but Kaluza, who's a brilliant thinker, doesn't think so. He becomes, unless this extra dimension is so small that we can't see it at all. It's like an infinitely thin straw. It's a line at a distance. On closer inspection, it had a surface. Then the geometry of space becomes 3. Our familiar large spatial dimension plus a curled up tiny dimension. So Kaluza wrote down the equations of general relativity in this space with the stroke of a pen. And he actually solved these seemingly more complex 5-dimensional equations. It was automatically separated and recombined like being enchanted. Present a completely different structure. It can be read as a purely 3-dimensional system of equations. Perfect description of general relativity in 3 dimensions. What's even more amazing is that it also pops up an additional set of equations to describe the new force. It's a force that's a little bit like a twin of the electromagnetic force. It even predicted new particles, and Kaluza discovered a shocking secret. The attractive force in 4-dimensional space, where the extra dimensions are too small to see, is equivalent to an attractive force in 3-dimensional space plus an electromagnetic force. What does this mean? The 2 fundamental forces of the universe, attractive force and electromagnetic force, unified in the higher dimensions, the kind of unification that physicists dream of. and he published this in the Proceedings of the Prussian Academy of Sciences. It was recommended by Albert Einstein himself, a theory that Einstein liked. Kaluza must be on fire now. And the reality is that almost no one listened to him, and they didn't for decades. Why was this incredible theory thrown into the cold? First, the war was raging and the order was shaky. The second is that the physics community is going through a real earthquake. In the 1920s and 1930s, quantum mechanics was exploited for the bizarre sights inside atoms. With all the brightest brains, the old foundations of physics are crumbling. In that era, as long as you're young and have the time and the brains to work on quantum quasi, yes, there's gold everywhere. In contrast, general relativity was profound, but at the time, even in 3 dimensions, general relativity can hardly find anything to match experiments. Now Kaluza has given him an even more mysterious 5-dimensional code. You said that in the hot age of quantum mechanics, who would leave a gold mine without digging? Instead of gnawing at the hard bone, the magical possibility of extra dimensions has been relegated to the fringes of science for nearly half a century. What was unexpected was that his rise came from another, even crazier theory. In 1984 in the United States, Peng's Physics Center physicists Michael Green and John Schwartz are one of the few who adhere to the theory of extra dimensions, and they came up with a key solution. This breakthrough solves a fatal problem that has long plagued the theory of extra dimensions. Turn the extra dimensions from a bench into a theoretical physics superstar overnight. There's a kind of a weird theory behind this. It started in the 70s, and it was self-consistent for its own sake. It seems that the extra dimensions require him to exist. String theory is heralded as a candidate for a theory of everything that could unlock the ultimate mysteries of the universe. String theory holds that the most basic units of the universe are not point-like particles. It's vibrating strings. The different vibrational patterns of these strings correspond to the different particles and forces that we observe. It's like the strings of a violin playing different pitches. And the vibrations of cosmic strings play the music of everything. The original theory was developed by Italian physicist Gabriele Necchi proposed in 1968, hoped to explain the strong interaction force. But after 5 years of painstaking research, physicists have discovered 2 major problems. One is that the predictions don't match the experiments. The second is also more lethal. If space didn't have 6 extra dimensions, it's mathematically incoherent. It just collapsed like a well-designed racing car without 6 wheels. This meant that by the early 1970s, the theory seemed doomed to fail. But a small group of physicists, including Green and Schwartz, they always thought there was some mathematical perfect cancellation in the theory, not a coincidence. They guessed, what if the theory isn't there to explain the strong force at all? Quantum theory of attractive forces. The ultimate theory that even Einstein remembered in his later years. This idea was very bold and almost unheard of at the time. After all, the quantum attractive force itself is a sinkhole theory and a black hole. Until 1980 for Green and Schwartz finally found the master key that can solve the problem of inconsistent calculation of apparent theoretical probability. They discovered an overlooked mathematical phenomenon in their calculation. All the trouble is gone after joining this baby elephant. The theory miraculously self-consistent. This is the famous Green. The Schwartz anomaly elimination mechanism, it's a stroke of genius in physics. And as that happened, it became apparent. This hard requirement requires an additional 6 dimensions of theory. Suddenly became the brightest white swan in theoretical physics. Countless physicists have flocked to this field for half a century. Physics of extra dimensions finally debuts in CEDIT. Physicists are trying to put together string theory with 6 extra dimensions linked to the more familiar 4-dimensional spacetime and the standard model. They believe that the particles and forces of our world are the result of the different vibrational patterns of the fundamental strings of the universe. And they need 10 dimensions. 3 spaces plus 1 time plus 6 extra spatial dimensions can fully vibrate. It depicts our reality. The pursuit of quantum attractive forces, Einstein's unfulfilled dream, has once again become the focus of physics. And the extra dimensions are the key to that holy grail. But the problem is that the theory requires these 6 extra unseen dimensions. What do they look like here? We'll have to call on our old friend geometry to solve problems on the cutting edge of the universe. It still needs to be used more than 2,000 years ago. Wisdom! When we look at the almost unimaginable 6 extra dimensions of apparent theory, it's like entering a Mobius strip. Klein bottles a labyrinth of these bizarre geometries. So we can ask, these 6 tiny extra dimensions, what can it curl up into? Is it simple geometry or unheard of? Weird enough to make mathematicians' scalps tingle. In the possible geometry of the extra dimensions, the most talked about is Calapichu Pop, named after mathematicians Calabi and Qiu Changtong. These spaces are treasures in a sea of mathematics. Mathematicians were intrigued by its beautiful yet extremely complex geometry. Imagine a typical Calapichu Pop. Possibly hundreds or thousands of high-dimensional versions of holes and handles. It's like a cosmic artifact made out of countless donuts and twists. They're mathematically miraculous. But why do physicists have such a soft spot for them? Why did the early salty theorists fall in love with these geometries? As a home for those 6 extra dimensions? Because they are so perfect together. A key reason is the geometry of these spaces. It seamlessly and automatically satisfies Einstein's equations of general relativity. The constitution of cosmic geometry. Calapichu is geometrically perfect, but that's not all. The classical theory of Einstein's equations does not include quantum effects. Usually the classical solution flips over once quantum effects are taken into account. Quantum effects bring uncontrollable extra energy. Smash the classic solution like a bare child driving the demolition team's big iron ball. In order to avoid this quantum pit, the classical solution of the quantum attractive force requires an additional amulet. And that extra symmetry that Calapichu geometry has exactly this kind of protection is called supersymmetry. That's a good thing. Particularly good at taming the wild horse of quantum physics. Basically, supersymmetry ensures that those pesky quantum effects split in two. The symbols are the exact opposite of each other. However, the fly in the ointment is that supersymmetry is still just a conjecture. It is difficult to say whether the universe has given him a hukou or not. When physicists in the mid-1980s. When I first encountered Calapichu, I was absolutely thrilled. Very few examples were known at the time. People once dreamed that this might lead to the only way to go. The old theory of 10 dimensions leads straight to the familiar 3-dimensional world and the standard model. Scientists had bold dreams. Are we about to touch the ultimate code of the universe? Unfortunately, reality soon poured a basin of cold water on such eligible Calapichu. The amount of space is not that sparse. Instead, it has sprung up like bamboo shoots after a rain, and it has grown so much that people are dazzled and their names sound very exotic. There are now billions of such geometries known, and we came up with an incredibly complex and elegant theory, but there's also a problem with baldness. The world we live in may not seem real at first glance. If these extra dimensions really exist, physicists believe they're everywhere. But it is even more tiny than dust. By some estimates, they're a quadrillion times smaller than an atom. What is that? It's when you magnify a grain of sand to the size of the Earth. The extra dimensions might just be an atom in the sand. So what if they're so small we can't see them? How do we know they exist? Or prove that these Carapichu are popular? Which are the extra dimensions of our universe really like? The more fundamental question is, it took so much effort. Talk about extra dimensions that we can't see, touch, or even imagine. What is the point of this itself? Is it just a physicist's ego? To answer this question, we have to first understand what it means to see something. Here's a joke about Richard Feynman, the genius of physics. It is said that Feynman once presided over the defense of his doctoral dissertation, a student who calculated a bunch of complex mathematical formulas. Feynman worried that he had gotten into the horns of mathematics and forgotten about physics. So I asked him, "Boy, what are the wavelengths of visible light?" The student stammered and said, I don't know. Probably. 1 meter Feynman boss went directly to the student and asked slowly, "Do I look confused in your eyes? The reason why we can see each other clearly?" It's because the wavelength of visible light is a little smaller than a micron. Anything much larger than a micron doesn't blur with visible light. And something much smaller than that, like atoms, it's blind with visible light. Atoms exist, but they're 1,000 times smaller than the wavelength of visible light. So it's impossible to see them with visible light. Visible light, this ruler is too thick. Even if we can't see individual atoms, but we feel their presence and influence all the time. If you don't believe me, try patting your thighs now. We don't go straight through the chair like ghosts when we sit down. It is because of the atoms that make up our bodies, and the invisible electrical interaction between the atoms that make up the chair. In hard-carrying for atoms. Even if we can't see them directly, we can actually feel their presence. Then for those extra dimensions that may be countless times smaller than atoms, could there be a similar chair effect? What if at the tiniest scales in the universe, space really does hide some secret geometry? This will affect us three-dimensional creatures on a larger scale. What are the effects that can be perceived? Could we feel something like an atom? Indirectly touching these hidden dimensions to understand this, we have to figure out what dimensions are first. We are all familiar with three-dimensional space. Up, down, left, right, front, and rear. You can simply understand dimensions as the number of individual coordinates you need to give to say exactly where something is. But what about for dimensions, or 5 or 9? Honestly, who can really imagine it in their head? What do the 9 perpendicular spatial dimensions look like? Just thinking about it is enough to make our three-dimensional brain. It's just not perfectly intuitive. But we can try to bring it a little bit closer. Imagine an ant walking on a vine. The vine is long and thin. For an ant, it can crawl forward or backward on the vine. It feels like this vine is mainly a line, a one-dimensional world, of course. If we look at the surface of the vine with a super microscope, you'll find that it's actually a two-dimensional plane. But what about ants? Although they are small, they are the thickness of vines. It's still so huge that it can barely feel the vines except to grow. In addition to this heterodimensional feature, there is the dimension of thickness. Actually, the surface of a vine is two-dimensional, but for this ant, that's big enough. All it can easily perceive is actually only one dimension. We think about the extra dimensions that might exist. Maybe it's as if this ant is measuring the thickness of a grapevine. If the extra dimensions really curl up small enough, then we. And all our current detection technologies, they're all too bulky to coarse. You can't even tell they're there. The vibrating fundamental strings of string theory may be small enough to dance in these extra dimensions. But we don't have the tools to resolve fine structures on a small enough scale. Imagine you're wearing thick boxing gloves and you're asked to build an elaborate Lego model. No door! But is there no clue at all? Could there still be some phenomena? Extra dimensions can pass through these phenomena, cleverly show us any hints of their existence. And even though we can't see their full, complex structure directly, the answer is yes, and this clue may lie in what we have already discovered, or examples that may be found in the future. Physicists who cannot directly resolve the complete geometry of the extra dimensions may perceive only a few rough features and shadows left by the extra dimensions. It's not that we have no information at all, it's that information can be very limited and indirect, metaphorically speaking. It's a bit like trying to write a dream of the red chamber with 100 characters. At energies far below the ability to directly see the fine structure inside the extra dimensions. The mathematics of Einstein's general theory of relativity, as a mysterious prophet told us, those extra dimensions curled up. They leave behind a residual effect or reverberation of the vibrations will take the form of particles we are familiar with, which means, if we don't have enough energy or detect, insufficient precision obscures the ability to perceive complex geometries with extra dimensions. So before these dimensions completely disappear from our view, the last things we can grasp are some examples with specific properties. This is derived from rigorous mathematical equations, and the math goes one step further. Examples of these extra dimensions, their number, variety, and how they interact faithfully reflect that. The geometry and topology of those hidden extra dimensions in general. The more complex the topology of the extra dimensions is, then the more kinds and numbers of particles survive in these dimensions. And these particles can be thought of as the hidden extra dimensions. The fundamental quantum excited state of geometry and the relationship between these particles and the extra dimensions in this theory. They're a little bit like the photon that we're familiar with and light and electromagnetic fields. A photon is a minimal quantization of the energy of an electromagnetic field. Particles from these extra dimensions is the smallest quantum legacy and surname of those high-dimensional attractive force theories in the low-dimensional world. So here's the problem again. What are these legacy particles that hold the secrets of extra dimensions? Can we observe them? If they do exist and are a universal feature of theories of extra dimensions, then we should be able to pull them out of the nooks and crannies of the universe. Don't worry. Scientists have their eyes on them for a long time. First of all, let's focus on one of the most interesting and representative classes of legacy particles. They're called magic particles. These magic particles, their names suggest their origins. They result from an accurate description of the size and shape of those extra dimensions that are curled up. They are, in a sense, the representatives of the geometry of the extra dimensions. They're completely trapped in those tiny extra dimensions, you might say. Wouldn't it be over to directly use the particle collider to knock these magic particles out? The idea is beautiful, but the reality is skinny. The problem lies in the noble lineage of these magic particles. They arise from the different vibrational patterns of the induced particles in the extra dimensions. So these magic particles behave in the same way as the attractive force, mainly through the attractive force interaction. And the attractive force is the most Buddhist and socially fearful of the four fundamental forces of the universe. Terribly weak. How weak is the attractive force? Let's just say you stick out your little finger now. A light tick can lift a heavy string of keys, right? In the process, that tiny bit of electromagnetic force from your little finger easily defeats the attractive force of the whole Earth on that string of keys. Therefore, the attractive force is too weak to any particle on our planet. None of the subcolliders can directly detect phenomena produced purely by the interaction of attractive forces. Examples where the strength of the interaction falls into the category of attractive forces, such as magic particles. Even if we let LHC run from the age of dinosaurs to the present, I'm afraid I can't hit a few. Their interactions are stronger than even the most mysterious ghost particles in the universe. Neutrinos are much weaker. Neutrinos can pass directly through the entire Earth without changing their face. The magic particles are more fearful than him. Then aren't we completely out of play? Could it be that extra dimensions and these mysterious magic particles? It's really just a physicist's pie. Will never be observed. Let's not jump to conclusions. Indeed, magic particles are very difficult to create in the first place because they interact so weakly. However, everything has two sides, and this weakness is both a disadvantage and an advantage. Once they're created, these magic particles can also live an extraordinary amount of time. The old birthday star of the particle world. The weaker the interaction, the harder it is for particles to decay. Those particles created by the strong interaction force, they don't normally survive a billionth of a second. And those magic particles that interact only through the strength of the attractive force, lifespan can be years or even longer. But here was the problem. If they can't be made in the lab, where can they be made? To make them, we need the most extreme conditions. So when in the history of the universe have such extreme conditions comparable to purgatory occurred? There is only one answer. At the very beginning of the universe, people believed. At the dawn of our universe. He went through a period of exponential expansion known as the cosmic explosion. During this time, the size of the universe has expanded dramatically at an eye-popping rate. For example, an instant that's much shorter than the time it takes for a beam of light to pass through an atomic nucleus. A region that used to be a tiny bit the size of an atomic nucleus will be blown up to be bigger than our entire body. The Earth is much, much bigger. The vast amount of energy contained in the universe when this violent period of explosion is over, like a flood opening a gate. From the mysterious blast site that drove the explosion, quickly transferred to a wide variety of elementary particles. That is, countless particles are created out of thin air. It also fills these newborn particles with unimaginably high energies. Right after the explosion, our universe was a pot of temperature and energy. It's all over the table. And these energies present during the explosion, it's inherently connected to the geometry of space. The geometry and attractive force of space and Einstein's general theory of relativity, almost two sides of the same coin. And the magic particle is the quantum excited state of the geometry of extra-dimensional space. So if magic particles really exist, then when the universe exploded, when the energy of the blast field is transferred to various particles like an annual bonus, these magic particles are the sons of extra-dimensional geometry. Naturally, there is no shortage of a piece of the pie. They also successfully shared the big red envelope of cosmic energy after they're being produced in large numbers, and they exist. And in that orgy of cosmic energy redistribution, take your place right here. The long lifespan of the magic particles finally came in handy in that hot cosmic soup. All kinds of particles are being produced and annihilated like crazy, but most of these particles are kind of passing by, and they have a very short lifespan. What about magic particles? By virtue of their weak to friendless interactions, will live much longer than most other particles. If this scenario is true, then over time, as other short-lived particles decay and disappear, these long-lived magic particles will gradually come to an end, and for a brief moment, it dominates the energy density of the universe. Cosmic energy, almost entirely in the form of these magic particles from the extra dimensions. And you can think of this process as taking a giant hammer, ring an ancient and huge bronze bell. At the moment it struck, the bells were loud and deep, full of rich slanting and overtones. But as time goes by, those high-frequency ramp waves that decay faster at higher frequencies will first disappear after a few seconds. All you can hear is the lower vibrations, the longest-lasting product frequency and low-frequency ramp waves, also in that chorus of energy in the early universe. After all other short-lived particles have decayed, the longest living and weakest interacting particles, like the magic particles, it's the last lingering sound. According to physicists, within minus 25 seconds of a single second after the Big Bang, the vast majority of species of particles have decayed into something else. But these old birthday devil particles can hold tenaciously for nearly a full V-second. A V-second in front of a U-second is a relative eternity. Now, you might say that even if the magic particles lived longer, it wouldn't seem like a big deal. Isn't energy conserved? When other particles decay, their intelligence doesn't just disappear, but will be converted into other forms of energy, especially relativistic particles like photons. That's true. But don't forget that our universe has been expanding rapidly since its inception. As the universe continues to expand, those relativistic waves, for example, energy in the form of photons, is rapidly dissipated due to the Doppler effect. The Doppler effect refers to the frequency of waves. Will change depending on whether the source is moving towards us or away from us. The classic example is the sound of an ambulance siren. The sirens would become sharper as the ambulances sped towards us. And as he's gone, the sirens get louder. What does this have to do with an expanding universe? For observers anywhere in the expanding universe, the universe is expanding as if every other place is moving away from you. In this case, all forms of relativistic wave energy will feel the cosmological rainbow shift brought about by the expansion of the universe. And as space gets stretched, the wavelengths of these waves get stretched. So their frequencies all continue to decrease for light waves. The energy of a photon is directly proportional to its frequency. So the frequency of cosmic expansion photons decreases. the photon's energy goes down and the energy is diluted. But for these old birthday mojitos, the situation is completely different. The magic is usually very heavy. Their energy is mainly related to their own resting mass. Rather than having to do with their state of motion, these heavy particles, it's not usually relativistic. They're just sitting there as the universe expands, until they finally decay. As space expands, these magic balls are like pebbles fixed to the surface of an inflated balloon. Their own mass and energy doesn't decrease because of the stretching of space at the same time. All those other examples that link most of its energy to high-speed motion, such as photons, their energy is constantly diluted and dissipated due to the Doppler effect. So if magic particles really exist as theory predicts, and were mass-produced in the early universe, then the universe is likely to be after the explosion. We went through a brief but crucial historical period in which the total energy density of the universe is mainly determined by the static, contributed by the mass of the heavy magic particle. That is to say, in that short time of nearly a microsecond at the beginning of the universe, these magic particles from the extra dimensions ushered in their unique highlight moment on the stage of cosmic history. They are everywhere. They are the masters of the universe. Almost all the energy of the universe is represented by these extra dimensions, exists in the form of quantum-excited megans. It's a universe ruled by dimensional ghosts. If all this is true, then the existence of such an early cosmic era dominated by mojitons will reduce the difficulty of detecting these extremely faint imprints of extra dimensions from that unreachable level of fantasy down to one, though still daunting, but physics puzzles that are at least theoretically promising. At least we know where to look for clues. So what to do? How can we detect that this might be caused by a short-lived magic particle? Dominant microsecond evidence, the answer? Could be hidden in their final curtain call. That's their decay. Despite their ultra-weak interaction of attractive forces, gives them a much longer lifespan than other particles. But these old-fashioned magic particles will eventually decay. Their vast store of intelligence would be converted into the familiar standard model particles. That ignited the hot Big Bang fire of the early universe. But it's also possible that as they decay, they'll produce a few more new and unknown particles not found in the standard model. After all, the attractive force is the most loving force in the universe. It interacts with all forms of matter and energy. Among such unknown particles outside the standard model is a high-profile star candidate. It's the axion that people believe but aren't 100% sure exists. If it exists, it's the chosen one to solve some of the great mysteries of the universe. If one magon decays into two axions, then each axion will acquire half the intelligence of the magic particle and travel freely through space at nearly the speed of light. The axions predicted to have very light interactions are also extremely weak, so that any axions created by the decay of magic particles in the early universe will be like lone rangers in the universe from the moment they are born. It has traveled freely to this day with almost no hindrance, and it forms a cosmic background of axion radiation. So the decay of those magnetons that might have been abundant in the early universe may have left us a permanent cosmic memento. A cosmic background radiation composed of countless relativistic axions. They're like ghostly stones from the beginning of the universe, carrying secrets from that distant era, passing us silently. This thing is not easy to detect. It is a million times harder than finding a needle in a haystack. A similar cosmic neutrino background radiation that we already know does exist. But to this day, scientists all over the world are lucky enough to catch only 1 or 2 a year. It's probably harder than that to detect the background radiation of axions, but it's hard. Doesn't mean it's impossible. Theoretical physicists point out that in a strong magnetic field, axions have a probability. Although it may be very, very small, a peculiar transformation can occur. Become photons that are easier for us to detect. It's like casting a travel restriction spell on these cosmic ghosts. Therefore, such a possibility originates from the cosmic axion background radiation from the decay of early cosmic magic particles. It would be possible, at least in principle, to set up powerful magnetic fields in the lab. Then we use extremely sensitive photon detectors to capture the faint photon signals that might be converted by axions. Therefore, it can be detected indirectly. In the future, as we build more sophisticated and larger telescopes and particle detectors, by carefully observing the deep sky of the universe that seems to be empty in strong magnetic fields, maybe we can find clues. Prove that our early universe was once filled with these quantum excited states of extra dimensions called magic particles. Maybe, just maybe, the answer to the universe in the near future. Maybe it won't be closed to us forever. Just like Einstein's general theory of relativity was born only 100 years ago, and he may actually have originated from this subversive conjecture of higher dimensional space. It's almost 100 years old. It's been like a magic magnet for the past 100 years, attracting generations of top physicists to obsess over it. But to this day, he is still largely stuck in the find. There is a lack of direct experimental evidence at the level of brilliant mathematical theory. Maybe those extra dimensions really fill us like air. And the reason why we don't perceive their existence, maybe it's just because of the senses and technological means of us three-dimensional creatures. They all seem too crude, too bulky to appreciate their delicate structures hidden at the smallest scales. If they do exist, they will be everywhere. Exists at every smallest point in our universe of space and time. It will be a miniature geometric picture of exquisite and cleverly curled up, quietly waiting for us to invent a powerful enough cosmic microscope to see their amazing beauty. And what lies behind them? The profound physics principles that could rewrite our entire physics textbook. And that day may be the beginning of our true understanding of the universe. But now I need to say goodnight and sweet dreams to you.